Okay, so in this lecture, what we will see, how to compute the inverse of DFT. We have already seen, given a vector, how to compute the DFT of that vector. Now, suppose you have been given a vector, you want to find out the vector for whose DFT is that given vector. So that is the inverse problem. So we already know that DFT can be written as, so suppose we have y is equal to DFT say R, this polynomial. So I know that this can be written as y0, y1 up to say yn minus 1. This vector can be obtained as 1 wn, wn2 goes w in n minus 1, then this is 1 wn square wn4 goes up to w2 n minus 1 n. So it is that you are multiplying with 2 all these elements here. The next row will have multiplication with 3 all the rows here, goes up to say this last one will be 1 wn n minus 1, everything you will multiply by n minus 1. So w n n minus 1 n minus 1. So these are the points in which you have evaluated the polynomial R. This is with R0, R1 up to Rn minus 1. The entire evaluation can be seen like this. See, how would you get y0? Take the first row with this. This will give you y0. Then take the next one. Y0, when will you get y0? When x is equal to 0. When you put x is equal to 0, this will give you, sorry, x not equal to 0, x equal to 1. That will give you nothing but R0 plus R1 up to Rn minus 1, that will give you y0. How will you get y1? You have to substitute x is equal to wn. That is nothing but R0 plus R1 times wn, R2 times wn square. It goes up to that, that will give you y1. How will you get y2? y2 is substituting x is equal to wn2. So that will be given by 1 R0, R1 times wn2, R2 times wn4, goes like this. So everything is multiplied by 2. So that's the way you get all the vectors of y. So entire thing can be written in this form. You are getting one vector from another vector using this matrix transformation. This is from simple algebra. How do you get from one vector to the other vector? You have to use a transformational matrix. The matrix is here, this one. This is the matrix. Now we have seen how to get, given R0 Rn minus 1, how to get y0 up to yn minus 1. But now our problem is, we have been given y0 up to yn minus 1, and this we know, we want to get what is R0 to Rn minus 1. So this is nothing but, suppose I call this one as Vn, we are trying to find out R is equal to Vn inverse y. So we are taking, suppose if you take the inverse of V, sorry, this is Vn inverse, and if you multiply it with y, you will get the vector R. So let us now look at how does this Vn inverse look like. The inverse matrix of this matrix. This is called van der Monde matrix, already we know. Now the inverse of this matrix, there is a claim. The claim is this, the first claim, that Vn inverse is nothing but 1 over n, and let me this time take a big matrix so that I can write 1 1 1 1. Next one is 1. This time Wn minus 1, Wn minus 2, everything is minus now, power is minus, Wn minus n minus 1. The next one will be 1, Wn minus 2, not 2, Wn minus 4. It goes up to Wn minus 2n minus 1. Goes like this. The last one will be 1, Wn minus n minus 1. Goes out like this, Wn minus n minus 1 times n minus 1. So it is almost like Vn, but everything, the power is minus. If you compare Vn, you will see the power is only getting minus here, everywhere here, and of course there is a 1 over n. So Vn looks like this. How do we prove this? So let us, yes, somebody has already suggested, you multiply Vn with Vn inverse, then you show that if Vn inverse is this and multiply with Vn, you get a right identity matrix. So let us see how do we do this. So Vn inverse and Vn, if I multiply, and if you see that the entries there, I can write this one as 1 over n, that is the 1 over n coming from Vn inverse, sigma j is equal to 0 to n minus 1. This is just a matrix multiplication. I am going to write in sigma form. Wn minus jk times Wn jl, where this k is running from, this is the row 1 up to n minus 1, and L is running from 0, 1 up to n minus 1. This is just a matrix multiplication. You write matrix multiplication each entry like this. You take the row of one matrix, multiply with column of another matrix. The row number is given by k here, column is given by L here, and k, L, L are varying like this, which are giving you all the entries of Vn inverse Vn. Alright, like you have already written, like C, suppose you are getting C is equal to A times B, two matrices A and B. How do you write? Cij is equal to sigma Aik times Bkj, where k is varying from some 0 to n. So exactly like this it is written here. Okay. Now if you manipulate this a little bit, you will see this is nothing but 1 over n sigma j is going from 0 to n minus 1. This is W n j times L minus k. K is going from 0, 1 up to n minus 1. L is going from 0, 1 up to n minus 1. Now this we know will be 0 if L is not equal to k. If L is not equal to k, then this quantity, already using the fourth formula of our properties of identity, you are taking a summation Wnj some k here which is non-zero. So that will be, summation will be 0, we already know using the fourth formula. So this is 0 if L not equal to k, and it is, if L is equal to k, this is 0. So this will give you 1. So this gives you a 1, because the sum will be nothing but n over n will give you 1. So this is 1 if L is equal to k, and this proves that Vn inverse Vn is a matrix where all entries are 0 except the diagonal elements, and which is exactly 1. That means Vn inverse Vn is an identity matrix. So that means Vn inverse is indeed an inverse of Vn. So this proves Vn inverse is indeed an inverse of Vn, the way we wrote Vn inverse. Okay. So this we know now, the inverse of Vn looks like exactly this, it looks very similar to Vn except a sign change. Now that will tell us that somehow we can use the FFT, the algorithm of FFT almost similarly, using some modifications in the FFT we will get the inverse. Yes, you have some questions? Sum is n because if it is 0, it is 1. So n summation of 1 is n, so n over n is 1. Okay, so suppose, so now we know if R is equal to dft inverse of y is given by where rk, we know this Vn inverse looks like this, remember here Vn inverse looks like this, and we know R is equal to Vn inverse times y. So I know Rk will look like, using that 1 over n sigma j is equal to 0 to n minus 1 Wn minus jk yj. This will be clear once you write it here. Look at this. You have y here, y0 up to yn minus 1, that will give you the r vector on this side. So if you write 1 over n, it gets, then take a row, multiply with this one, you will get, say, take the kth row, multiply with this one will give you rk, and that is nothing but expressed in this summation here. This, the kth row is Wn minus jk times yj. J is running from 0 to n minus 1. This is the kth row. So this is the yk, sorry, this is the rk. And if you go back for dft, what, suppose y is equal to dft of r, dft of p, what did we have? In that case we have that this formula, yk is equal to j is equal to 0 to n minus 1 yjk n pj. That was the formula for dft of p. You just put the value of wnk of x and you will get yk is equal to. So this I am writing just to tell you the similarity between the formula. The only difference is minus here, there is no minus here, and there is of course a factor of 1 over n. Otherwise it is very similar. So this suggests that the algorithm of our FFT for the forward transformation also probably can be used with this very minor change even for inverse DFT, and that is what we will see. So remember, we are trying to find out R from Y. Y has been given to us the values, and we are trying to find out R. Now you form a new polynomial yx, just assume a new polynomial yx which looks like y0 plus y1x up to yn minus 1 x n minus 1. Just assume this polynomial, and again split this polynomial into two parts. y0x is equal to y0 plus y2x y4x square goes up to y n minus 2 x to the power n minus 2 by 2. Just previously what we did for p, we are doing it for y. Similarly, y1x is equal to y1 plus y3x y5x square goes up to y n minus 1 x n minus 2 by 2. Just splitting into two parts, just before, as before we did for p, we are doing it for y here. Now remember, now you see again yx can be written as y0x square plus x times y1 x square. We can write yx like this, just like we did for p. Okay. So remember again, let me repeat, we are trying to get the vector r from given y. So this is a polynomial we are just forming for our convenience. Okay, then we have divided into two parts and written the yx like this. Let's see how can we use this now. What we will do, we compute recursively R0, the first part, which is nothing but DFT inverse of y0, that is the first part of y, one part of y, and we will put R1 which is nothing but DFT inverse of y1. Okay, this is a recursive definition, recursive call actually it will be. Now let me write the formula for R0k. So n times R0, the kth element of R0. This is a vector of n over 2 elements, right? Here we have split it up to n over, sorry, n minus 2 over 2. So there are n over 2 elements here, n over 2 elements here. So again we need up to n over 2 with root of unity, just like the previous one. So R0k, I can write this one as y0 wk n over 2 for 0k going up to n over n minus 2 over 2. So let us see, before I proceed further, why can I write this? Look at the formula of R. Look at the formula of Rk. Here is the formula of Rk. Rk is 1 over n sigma j going from 0 to n minus 1 this. Now n Rk is nothing but sigma of this. Now sigma of this is, you will get the sigma of this if you put x is equal to w n minus k. If you put x is equal to w minus k n, then this sum is exactly this sum. So this is nothing but as if you are evaluating this polynomial at x is equal to w n minus k, as if. So that gives you nRk. And similarly, you will see nRk0 is exactly, you are evaluating the polynomial y0 at this, at wk minus n square, because you are going to put n x square, and that will give you already minus kn over 2 here. So similarly, I can write n times rk1 equal to y1 w n over 2 minus k for 0k n minus 2 over 2. So these are the two things we know. Now I want to see how can we get the vector r from these two. This is r0 and r1. I have to compute r basically, just like the previous one. We computed y0 and y1, then computed y out of it. So this time also we have computed r0, r1, we will compute r out of it. Now let us see how do we do this. So I go to the next one. So for 0k going up to n minus 2 over 2, n times rk, we can see this is nothing but y by our observation, previous observation. If you evaluate y at yn minus k, you get n times rk. Already you have seen this. This is, I can write as y0 wn to k. Why? Already we have expressed yx is equal in terms of y0x and y1x by that formula. I am going to use that formula now here, this formula. Yx is in terms of y0x square plus x y1x square. This formula we are going to use now. So this is yx, x is equal to wn minus k. Using that formula, this is nothing but y0 wn minus k square. That will give you minus 2k plus w plus x, which is wn minus k, y1 evaluated at the same point, again square, wn minus 2k. This already we have seen, this is nothing but nRk0 plus wn minus k. This already we have seen is nothing but nR1k. So I can compute the Rk from 0 to n minus 2, that's first half of R, using this formula. You can see all n goes out, so I know that Rk is equal to Rk0 plus wn minus k RK1. So this is the formula for the first half of K, first K of R. Now definitely I have to do the next one. Next one is n times R K plus n over 2, the next half of R. This is again, I just straightforwardly, if you put Wn minus K plus n over 2, I am just substituting this value. Instead of K, now it should be K plus n over 2, that is what I have done. So y of this is again using that formula of Yx, is straightforward substitution, y0 Wn, if you take the square of it, what do you get? Wn minus 2k minus n. The Wn minus n, that is 1. So that is nothing but Wn minus 2k, it remains, plus that x part, which is nothing but Wn minus n over 2 plus k, that is the x, this one, times y1, which is again by the same trick will be nothing but Wn minus 2k. Now this you can write, this part is nothing but n times Rk0, we have already seen this, like here nRk0, here also this is nRk0, plus now Wn minus n over 2 plus k, this is nothing but minus of Wn minus k. This is true. Now this, once I have written this, and this part already we have seen is n times R K 1. Again all n's cancelled out. So if the next formula you get, is R K plus n over 2 is equal to R K 0 minus Wn minus k R 1k. So this will give you the next half. So this is the first half of first k values, n over 2 values of R. This is the next n over 2 values of R. And you will see, if you go back in the previous lecture, your computed value of y, the first n over 2 values of y had exactly similar formula. Also this one was exactly same formula, except instead of Wn minus k, it was Wnk. If you go back and check in the previous class's formula, there in the DFT version, Yk was nothing but P0k plus Wnk P1k. Here only instead of Wnk we have Wn minus k. Similarly here. So the algorithm for computing the DFT remains exactly same. Only thing you have to change now, instead of Wnk you have to use Wn minus k. So that gives you, one algorithm gives you both inverse and forward, but only thing is, only change will be changing at that places. So we can compute. Now I am going to conclude. So we can compute R by R is equal to 1 over FFT inverse Y, where FFT inverse is different from FFT only at two places. In line 1, I did not note the line 1. That is where we were putting Wn is equal to I twice pi by n. This you replace by Wn inverse, where you use e to the power minus I to pi over n. You are initializing Wn is equal to e to pi I over n. Here you just initialize with this. And there is another place, line 2, where you need to change W is equal to W times Wn, that you write W is equal to W times Wn inverse. actually this actually you don't need to change this line. If you initialize your Wn is equal to this is automatically taken care of, because every time you are multiplying with Wn, your Wn is already defined like this. So this will take care of it. So this actually this is the only change which is needed. Nothing else is needed for you. So this will give you the inverse of your DFT. And remember, you have to take 1 over n, because if you go, if you check that Vn inverse is actually 1 over n times that matrix. So 1 over n factor is remaining. So that you have to do, take care here. So again this entire algorithm will run in n log n time, because of the same reason, because we have not changed the algorithm at all. Only some constants we changed. But all these manipulations told us that the algorithm must have to remain same, only by changing only a little bit we get two operations which are exactly opposite of the other. So let me summarize. So this is the summary. Let Px and Qx be two polynomials with degree bound n is equal to 2 to the power k. Then R is equal to DFT inverse 2n equal to DFT 2np times DFT 2nq, that's it, is such that Rx is equal to Px times Qx, and it can be computed in order n log n time. So the entire procedure is, first you take DFT of P, DFT of Q, step 1 in n log n time, multiply the 2 in order n time, take the DFT inverse in n log n time, you get the coefficient R for the resulting polynomial, where resulting polynomial Rx is equal to Px times Qx. So this is the, and this entire thing can be done in n log n time. So that is what is we will cover in DFT and FFT. Okay.